Welcome to another episode. Wherever you are, maybe resting in bed, maybe letting the day slow down, this is your time to listen. To drift with a story that begins not with machines or numbers, but with something we've all felt, warmth and cold. If you'd like, you can let me know in the comments where you're listening from and what time it is there. I always enjoy seeing how these stories reach people across different places and moments in the day. And if you find yourself returning here, you might think about subscribing. It's a simple way to stay connected whenever a new story arrives. For most of human history, words were all we had for temperature. We spoke of frosty mornings and sweltering afternoons, of mild breezes and bitter nights, a hand on the forehead, the comfort of a fire, the sting of ice water. That was how people knew heat and cold. Not in numbers, but in sensations. And yet, slowly, we learned to measure the invisible. A thin column of water rising and falling in glass. A bubble of air trapped and shifting. Later, a drop of shining mercury creeping along a scale. From those fragile beginnings came the devices we call thermometers. Tools that turned the vague into the precise, the fleeting feeling of too hot or too cold into something we could share, compare, and trust. Tonight, we'll follow that story. From wine-filled tubes to Galileo's early experiments, to Fahrenheit's curious choice of 32 and Celsius's elegant 0. Along the way, we'll step back into a world before anyone knew what the exact temperature was, and reflect on how much clarity a simple glass tube has given us. So if you're ready, let's begin. Before glass tubes, mercury scales, and neat rows of numbers, people knew temperature in the most direct way possible, through their bodies. To feel the world was to measure it. Heat and cold were not abstract values, but sensations that pressed themselves into skin, bone, and breath. A frosty morning was felt in stiff fingers, in the whiteness of breath, in the heaviness of a frozen bucket drawn from the well. A summer's heat revealed itself in sweat, in the lethargy of animals, in crops that wilted or thrived depending on how relentless the sun had been. For millennia, human beings relied on these senses as their only barometer. Entire civilizations functioned with no precise notion of what we today call degrees. They didn't know that water freezes at 0 degrees Celsius or 32 degrees Fahrenheit. They knew only that ice formed, that fires burned, that wine soured when the cellar grew too warm. In ancient Mesopotamia, scribes recorded the flooding of the Tigris and Euphrates, and priests observed the shifting winds. But there was no instrument to pin down the subtle change between cool and chilly. In Greece, philosophers such as Aristotle wrote about qualities, hot, cold, wet, dry, as fundamental to nature. Medicine, in particular, was built on these qualities. Hippocratic physicians judged fevers by touch, a palm against the forehead, a hand clasped around the wrist. A patient wasn't 38 degrees Celsius, but burning hot or slightly warm. This world of impressions shaped how people thought about health and disease. Illness was explained through imbalances of humours, blood, phlegm, yellow bile, and black bile. Heat was not something to measure. It was a property of the body itself, a sign that the vital forces were stirred or disturbed. A sweating fever meant the body was expelling excess. A chill meant the balance had been disrupted. Without instruments, such judgments were subjective, a matter of experience, intuition, and comparison. One healer might say the patient felt dangerously hot, while another might say it was only moderate. The body of the healer became the first thermometer. Outside medicine, heat and cold were woven into daily survival. Farmers in medieval Europe timed their planting not by exact temperatures, but by signs in nature, when swallows returned, when blossoms appeared on apple trees, when the soil felt warm enough beneath the hand. Sailors judged storms not by barometric readings, but by how the air thickened, how winds shifted, how clouds piled on the horizon. A fisherman in the North Sea did not need to know the water was 9 degrees Celsius. He knew only that the sea was biting, that staying too long meant frostbite and death. Winemakers and brewers, too, lived in this world of approximation. Fermentation is deeply sensitive to temperature, but medieval brewers had no dial to guide them. They relied on rules of thumb. Yeast should be added when the wort felt neither hot nor cold to the touch, blood warm. Some instructions from the 16th century brewing texts advise that if you could comfortably dip your finger into the liquid, it was ready. In effect, the brewer's finger was the thermometer, and consistency depended on generations of experience. Still, there were glimmers of curiosity, attempts to build something more consistent than the human hand. As early as the 1st century CE, the Roman engineer Hero of Alexandria described devices that responded to changes in heat and cold. One of his inventions used air trapped in a globe above a tube. When warmed, the air expanded and pushed water down the tube, making a fountain rise. It was a marvel, but it wasn't used as a practical tool for measurement. It was theatre, a demonstration of nature's hidden forces. In the centuries that followed, scattered hints of similar devices appeared. Islamic scholars during the Golden Age described water clocks and clever automata powered by changes in air and water, which sometimes incidentally responded to temperature. These were not yet thermometers, but they revealed a dawning awareness. Heat could move matter in predictable ways. By the Middle Ages in Europe, most people still spoke of temperature only in words. Chronicles mention the bitter cold winter of 763, or the blazing heat that ruined the harvest of 1315. These were remembered through suffering, through floods, famines, and frosts, not through precise records. For everyday people, temperature was simply life as it was lived. Whether your food spoiled, whether your child survived the fever, whether the river froze thick enough to cross. What makes this period so fascinating is not what they lacked, but how they adapted. In the absence of instruments, culture filled the gap. Languages developed a rich vocabulary of climate and sensation. In Old English, there were dozens of words for cold, each carrying its own nuance: sealed, night-shield, forced, snort-sealed. Poets used these not to describe numbers, but experiences, the way cold penetrated the bones, the way frost glittered under moonlight. Heat, too, was described poetically: sultry, stifling, scorching, sweltering. Our ancestors may not have had thermometers, but they had metaphors that mapped directly to lived sensation. Yet behind this world of sensation, a question quietly grew. Could heat be measured? Was it possible to move from metaphor to number, from feeling to scale? Renaissance Europe, with its thirst for experimentation, began to ask these questions more seriously. Glassblowers in Venice and Florence were perfecting their art. Scholars were questioning Aristotle's framework of qualities. And in this environment, a new kind of device appeared. Fragile, simple, but transformative, the thermoscope. But before we step into that invention, it's worth pausing. Imagine a world without temperature readings. Imagine waking with a fever, and your doctor placing a hand on your brow, then nodding gravely, with no further quantification. Imagine storing wine, brewing beer, or curing meat without knowing the exact conditions, relying only on touch, taste, and smell. Imagine farmers debating whether the soil was warm enough for seeds, each with a different answer, none with numbers to prove their case. It was a world of uncertainty, but also of intimacy. To feel the environment was to be bound to it directly. The air on your skin, the chill in your bones, the heat of your hearth. These were the instruments. In some ways, life was guided not by numbers, but by a visceral sense of connection to nature. Still, as with so many human endeavors, the desire to bring order out of sensation persisted. The body alone was not precise enough. Two doctors disagreed. Two farmers felt different things. Words could be poetic, but they could not be standardized. And so, slowly, a quest began. To trap the invisible, to coax heat and cold into a glass vessel, to make sensation into measurement. That quest would begin in earnest with Galileo and the fragile device he called a thermoscope. By the turn of the 17th century, Europe was alive with curiosity. The Renaissance had stirred minds across the continent. Old authorities were being questioned, and new instruments were being made to reveal the hidden structure of the world. The telescope opened the heavens, the microscope peered into the small, and somewhere between these two frontiers, the thermoscope was born. Galileo Galilei is most often remembered for tilting his telescope toward the skies in 1609, revealing mountains on the moon and moons around Jupiter. But around the same time, he was also experimenting with heat and air. To him, heat was not just a quality one could feel. It was something physical, something that could move matter. If it could move matter, perhaps it could be measured. The instrument he devised was deceptively simple. Imagine a narrow glass tube, one end sealed into a small bulb. The open end was placed in a vessel of water or wine. When the bulb was warmed, perhaps by holding it in the hand or by moving it near a flame, the air inside expanded, pushing some of the liquid down the tube. When the bulb cooled, the air contracted, and the liquid climbed back up. The height of the liquid column shifted with temperature. It was, in essence, a primitive thermometer. But it wasn't yet a thermometer as we understand it. Galileo did not calibrate it to fixed points. There was no 0, no 32, no 100. It simply showed change. Warmer meant the liquid dropped lower. Cooler meant it rose higher. It was a relative scale, not an absolute one. For this reason, it is more accurate to call Galileo's device a thermoscope rather than a thermometer. The brilliance of the thermoscope lay in its elegance. Heat and cold were no longer vague sensations or poetic descriptions. They had become visible in glass. Anyone could watch the liquid move and agree that something was happening. The invisible had been given a kind of body. And yet, the device had deep limitations. Because the system was open to the air, it did not just respond to temperature, it also responded to pressure. If the barometric pressure shifted, say, before a storm, the column moved, even if the temperature remained constant. A cool breeze might push the water in one direction, while humidity could cause another effect. The readings were not stable across different places or days. What seemed like a thermometer was in truth an instrument sensitive to multiple forces. Still, in the early 1600s, this was revolutionary. For the first time, there existed a tool that could show the gradations of warmth and cold without relying solely on the senses. Galileo's pupils, including Benedetto Castelli and Santorio, began to explore its possibilities. Santorio, a physician from Padua and a contemporary of Galileo, was especially intrigued. He adapted the thermoscope for medical use, placing it against patients and noting how the liquid shifted. Santorio is often credited as the first to use a temperature-related device systematically in medicine. He was also obsessed with measurement in general. He weighed patients before and after meals, charted their weight over months, and sought to understand the balance of intake and output in the body. For him, the thermoscope was one more tool in a broader philosophy, that the body could be quantified. This was a radical departure from the older, humoral medicine. Instead of vague talk of fevers, Santorio believed one could describe illness with something closer to numbers. He could not yet say, the patient has 38.5 degrees Celsius, but he could say, the patient's heat is greater today than yesterday, as seen in the rising column of liquid. That shift, from impression to visible evidence, marked a profound change. Elsewhere, others were experimenting with their own versions of the thermoscope. Giovanni Francesco Sagredo, a friend of Galileo, is said to have built instruments that relied on wine rather than water, since alcohol expanded more predictably with heat. In Florence, members of the Medici court tinkered with variations. Across Europe, the idea spread. Heat could be captured, seen, perhaps even compared. But the lack of standardization made comparison difficult. If one physician in Padua noted that the water had risen 3 fingers in his glass, and another in Paris observed 2 inches in his, what did that mean? Without fixed reference points, each thermoscope was its own little universe, useful locally but impossible to translate across distance. And then there was the problem of air pressure. It wasn't until Evangelista Torricelli, Galileo's student, invented the barometer in 1643 that the influence of air pressure was fully appreciated. Before then, thermoscope users were mystified by the irregularities. Why did the column sometimes rise on a cool day? Why did it fall on a warm one? The concept of atmospheric pressure was not yet widespread, so these fluctuations seemed puzzling. Despite these flaws, the thermoscope carried symbolic weight. It embodied the Renaissance spirit of making the intangible tangible. Just as Galileo's telescope had shown craters on the moon that no eye had ever seen, the thermoscope showed gradations of heat no hand could precisely feel. Both instruments extended the senses, bridging the gap between perception and knowledge. It is worth pausing to imagine what this must have felt like. A scholar in a dim Italian study, holding a fragile glass tube, watching a little bead of wine rise and fall as if animated by some invisible force. Heat, once nothing more than a sensation in the body, now seemed like a thing that could push, expand, and move. The world was revealing itself in new ways. But in the story of thermometers, the thermoscope is a threshold, not the destination. It showed that measurement was possible, but it did not yet offer reliable numbers. It inspired fascination, but also frustration. Scholars began to ask, could there be a way to seal the system, to make it independent of the open air, to fix a scale that anyone could use anywhere? That question would drive the next century of experimentation. By the mid-1600s in Florence, members of the Accademia del Cimento, the Academy of Experiment, built sealed liquid thermometers using alcohol. By the early 1700s, mercury would replace alcohol for greater stability, and by the mid-18th century, Daniel Gabriel Fahrenheit and Anders Celsius would introduce the fixed scales that survive to this day. Yet the humble thermoscope deserves to be remembered. It was not precise, it was not standardized, but it was the first step toward the modern language of temperature. It transformed sensation into signal, impression into evidence, and in doing so, it set the stage for centuries of science to come. Reflecting on it now, the thermoscope feels almost poetic. A small bubble of air, trapped in glass, expanding and contracting with the warmth of a hand. A little column of wine, slipping up and down as if breathing. It was fragile, imperfect, easily fooled by the weather. But it carried within it a promise that heat, like light or sound, could be measured, studied, understood. The journey from that fragile column to the precise scales we know today was long and complex. But the spirit was there, the idea that the invisible could be made visible, and that the shifting warmth of the world could one day be written in numbers. The early thermoscopes of Galileo and his circle had revealed something extraordinary. Heat could move matter in predictable ways, but they were imperfect, unreliable, and untrustworthy across different places and times. If science was to progress, if physicians were to compare symptoms across Europe, if natural philosophers were to share experiments and observations, then there needed to be something more stable than a rising bead of water in an open tube. The 17th century was an age of refinement. The telescope and microscope had already shown the power of glass to extend the senses. Now, the same material would be called upon to tame temperature. The first major leap was simple, yet profound: sealing the instrument. By enclosing the liquid inside glass, with no open contact with the air, the thermometer could be freed from the fluctuations of atmospheric pressure. The expansion and contraction of liquid would now reflect temperature alone. In Florence, members of the Accademia del Cimento, a society of experimenters founded in 1657 under the patronage of the Medici, were among the first to build sealed thermometers. They used alcohol, colored with dye, so the movement of the liquid was easy to see against the glass. Alcohol was more sensitive than water, expanding and contracting dramatically with small changes in heat. Yet alcohol had its weaknesses. It evaporated easily, and different mixtures expanded at slightly different rates. Worse, alcohol froze in the harsh winters of Northern Europe, leaving the scale useless in the very conditions where people most wanted to measure cold. A better substance was needed. That substance was mercury. Silvery, heavy, and fluid, mercury had long fascinated alchemists. Unlike alcohol or water, it remained liquid at extreme cold, only freezing at -39 degrees Celsius, -38 degrees Fahrenheit. Its boiling point, at 356 degrees Celsius, 673 degrees Fahrenheit, was far beyond anything a physician or craftsman would encounter in daily life. This made mercury uniquely suited for measurement. Mercury's other advantage was its predictability. It expanded evenly with heat, allowing for precise and repeatable scales. And because it was opaque and metallic, its shining bead could be read easily against the etched glass. The transition from alcohol to mercury did not happen overnight. Glass blowers had to perfect the delicate art of sealing the heavy liquid without trapping bubbles. Scholars debated which liquid gave more accurate results, but by the late 1600s, mercury was emerging as the standard. One of the key figures in this journey was Evangelista Torricelli, Galileo's student and successor in Florence. Torricelli is most famous for inventing the barometer in 1643, proving that air has weight and pressure. His work revealed why Galileo's thermoscopes had been unreliable. They were influenced not just by temperature, but by the invisible force of the atmosphere itself. By sealing liquid in glass, Torricelli and his contemporaries helped separate temperature from pressure. In doing so, they laid the foundation for true thermometers. Torricelli may not have built a mercury thermometer himself, but his experiments were crucial in shaping the understanding that would make them possible. In the early 1700s, the German physicist Daniel Gabriel Fahrenheit transformed thermometry from a curiosity into a practical science. Born in Gdansk in 1686, Fahrenheit traveled widely across Europe, absorbing the work of Dutch, German, and Italian glassmakers. In 1714, he introduced his mercury thermometer, stable, precise, and reliable across seasons. But Fahrenheit's true innovation was not just the use of mercury, it was his scale. He wanted numbers that could be replicated by any careful observer. To do this, he chose reference points. His lower fixed point was the freezing mixture of water, ice, and salt, a temperature colder than natural ice, consistent across experiments. He called this 0. The freezing point of pure water became 32. The temperature of the human body he set near 96, later adjusted to 98.6. The boiling point of water fell at 212. This gave him a scale of 180 degrees between freezing and boiling, conveniently divisible, allowing for fine measurements. Why 32? To modern minds, it seems awkward, but to Fahrenheit, it was practical. He wanted to avoid negative numbers in everyday use, and the salt-ice mixture provided a reliable anchor below freezing. By shifting his scale upward, he kept ordinary weather and medical conditions in the positive range. The Fahrenheit scale spread quickly in the German states, the Netherlands, and England. Its precision made it beloved by scientists and physicians. Even today, in the United States, Fahrenheit survives, cherished for its finer subdivisions, a difference of 1 degree feeling more meaningful than the broader steps of Celsius. But in Sweden, another thinker was seeking something simpler. Anders Celsius, an astronomer in Uppsala, proposed in 1742 a scale with just 2 fixed points, the freezing and boiling of water. He set boiling at 0, freezing at 100, an inverted scale where higher temperatures meant lower numbers. After his death, colleagues, including the botanist Carl Linnaeus, reversed the scale to the version we know today, freezing at 0, boiling at 100. The Celsius scale, with its clean decimal simplicity, became the natural companion to the metric system, where Fahrenheit's 180 divisions were practical for fine weather observations. Celsius's 100 were elegant, aligned with the spirit of Enlightenment rationality. By the late 18th century, Europe had 2 main thermometric languages: Fahrenheit, favored in the English-speaking world, and Celsius, spreading with the metric system across continental Europe. Both owed their possibility to the sealing of liquids, the choice of mercury, and the insights of Torricelli and his successors. What these developments achieved was not just technical precision, but shared experience. For the first time, a physician in London could compare a fever to one measured in Berlin, and both would know they were speaking of the same degree. An astronomer charting the weather in Paris could compare notes with one in Florence. Standardization made temperature a universal language. Before, cold was subjective. Now, 0 meant ice. 100 meant boiling water. The invisible had been given coordinates, and with those coordinates, new worlds opened. Meteorology blossomed as observers shared data. Medicine grew more precise, with fevers classified by degree. Industry learned to regulate processes with repeatable heat. Even daily life changed. Farmers knew when frost would strike, brewers controlled fermentation, households could compare one winter to another. It is striking to think that what we take for granted, glancing at a small glass tube and seeing a number, is the result of centuries of trial, error, and invention. From Galileo's open thermoscopes to Torricelli's understanding of air, from Fahrenheit's pragmatic salt mixture to Celsius's elegant decimals, the thermometer became a symbol of the human desire to give order to sensation. What had once been a matter of touch and metaphor became something quantifiable, universal, and shareable. Heat and cold were no longer just stories told in words, but realities captured in glass and mercury, etched into scales that crossed borders. When we glance at a thermometer today, its numbers seem natural, inevitable, as though they were always waiting to be discovered. But every number we see, every 32 or 0 on those familiar scales, was once a choice, a decision by a human mind, guided by logic, circumstance, and sometimes sheer practicality. To understand why the scales of Fahrenheit and Celsius look the way they do, we need to step into the workshops and studies of the 18th century when those choices were being made. Daniel Gabriel Fahrenheit, working in the early 1700s, wanted a thermometer that was precise, reproducible, and useful in everyday life. Earlier devices had shown relative change, but he wanted fixed points that any craftsman or scholar could replicate. His solution was to anchor his scale to 3 reference points. The first was a mixture of water, ice, and salt, specifically ammonium chloride or sea salt. When combined, this mixture reliably reached the coldest temperature that was easy to produce in a simple laboratory. Fahrenheit chose this as his 0. It was practical. Anyone, anywhere in Europe, could reproduce that icy brine and find the same starting point. By setting 0 here, he also ensured that his scale avoided the inconvenience of negative numbers in most ordinary situations. The second reference point was the freezing of pure water. In his system, this came out at 32. Why not 0? because 0 had already been claimed by the salted mixture. The distance between that mixture and fresh ice happened to be 32 divisions on his glass tube. Instead of renumbering, he preserved it, letting 32 mark the freezing of water. This quirk, born of convenience, became permanent. His third anchor was the temperature of the human body. To Fahrenheit, this seemed a natural point of reference, constant, familiar, and universally relevant to physicians. He initially marked it at 96. Later refinements adjusted it closer to 98.6, but the original placement reveals his thinking. Between the freezing of water at 32 and the warmth of the body at 96, there lay a neat, divisible interval of 64 degrees, a number he favored because it could be divided evenly many times. This made it easy to construct thermometers with consistent graduations. From there, the boiling point of water landed at 212. It may seem arbitrary, but it fit his design. Between freezing at 32 and boiling at 212 lay 180 degrees, a span that divided cleanly for practical measurement. Where older systems had struggled with irregularities, Fahrenheit's scale was crisp, replicable, and mathematically convenient. And so his numbers, 32, 96, 212, settled into glass tubes across Europe. To a modern eye, they look awkward, but to an early 18th century scientist, they were brilliantly functional. The mixture of ice and salt gave a reproducible low. The freezing of water gave a universal middle. The human body provided a medical anchor. Together, they created a system that worked in laboratories, hospitals, and households alike. Meanwhile, in Uppsala, Sweden, Anders Celsius approached the same problem from a different angle. An astronomer by training, Celsius was accustomed to thinking in terms of celestial cycles and universal constants. In 1742, he proposed a scale rooted not in salt mixtures or the human body, but in the properties of water itself. Water froze, water boiled, two clear universal events, unambiguous to anyone who could light a fire and melt ice. Celsius originally set boiling at 0 and freezing at 100. His reasoning was partly practical. By making higher temperatures lower numbers, he could avoid negative values for Sweden's cold winters, since everyday readings would fall between 0 and 100. In his writings, he emphasized the repeatability of these points under controlled pressure, an astronomer's insistence on precision. But after his death, his colleagues saw the scale differently. Carl Linnaeus, the great Swedish botanist, found it more intuitive to let higher temperatures correspond to higher numbers. Plants thrived in warmth, ice vanished in heat. Surely the numbers should climb upward with the temperature. And so, around 1745, the Celsius scale was inverted. Freezing became 0, boiling became 100, and the system we know today was born. This simplicity had an elegance that resonated with the Enlightenment spirit. Decimal divisions were already shaping weights and measures. 10 fingers, 10 divisions, 100 degrees between freezing and boiling. It felt natural, rational, and modern. Where Fahrenheit's 180 degrees between freezing and boiling required fractions for many calculations, Celsius offered clean decimals. For scientists, the appeal was irresistible. The two scales spread along cultural lines. In England and its colonies, Fahrenheit's system endured, woven into medical practice, household weather reports, and industry. In continental Europe, Celsius rode the wave of the metric revolution, aligning with a broader vision of standardized, universal measures. By the 19th century, Celsius had become the international scientific standard. Fahrenheit, however, persisted in daily life, especially in America, where it remains beloved for the way its smaller divisions capture subtle differences in weather and comfort. The slow march toward consensus was not simple. For more than a century, travelers and scientists had to translate between scales. A German physician writing of a fever at 40 degrees meant something far more serious than an English doctor recording the same number. tables of conversion appeared in scientific handbooks. Instruments were sometimes double-marked. Confusion lingered until the late 19th and early 20th centuries, when the metric system spread more widely and Celsius gained dominance in science and international standards. Yet even now, both systems survive, each carrying the legacy of its creator's vision. Fahrenheit reflects the pragmatism of an experimental craftsman, grounded in mixtures, bodies, and divisible intervals. Celsius reflects the clarity of an astronomer, anchored to universal properties and the simplicity of decimals. It is worth pausing to reflect on how human these numbers are. They were not handed down by nature, but chosen. One man's decision to call salted ice 0, another's to make boiling water 100. They are conventions, agreed upon, refined, and spread by consensus. And yet, through those choices, we have learned to speak a common language about one of the most intimate aspects of our lives, the feeling of warmth and cold. Without them, fevers would still be judged by the hand, weather by adjectives, seasons by metaphor. With them, we can share precise experiences across continents. A scientist in Delhi, a doctor in Berlin, a farmer in Kansas, all can speak of temperature in numbers that carry meaning beyond their own sensations. The journey from salt and brine to freezing and boiling is a reminder of how science evolves, not always through perfect logic, but through choices that balance practicality, intuition, and the possibility of shared understanding. Fahrenheit's 32 and Celsius's 0 are milestones not just in measurement, but in the history of human collaboration. The numbers may seem arbitrary, but behind them lies a story of ingenuity and consensus, of how we turned the shifting warmth of the world into something we could all agree upon, 1 degree at a time. Before the thermometer, heat and cold belonged entirely to the language of sensation. People spoke not of numbers, but of experiences. A morning was crisp, a breeze was biting, a summer's day was sweltering, and a night could be bitterly cold. Words carried the weight of temperature. Frosty meant more than just icy surfaces. It was a feeling that clung to one's bones, that stiffened the fingers and painted windows white. Sweltering suggested not just heat, but the languor of bodies too tired to move, the heaviness of air that seemed to press down upon the chest. Mildness was prized, a word that meant comfort, a gentle climate where neither fire nor heavy cloak was required. Language was a thermometer of its own, rich and descriptive. In Old Norse sagas, winters are described as iron cold, while in Middle English poetry, heat is compared to burning noon. These descriptions reveal how people lived with temperature, not as a scale, but as metaphor. The experience of weather and climate was embedded in storytelling, in memory, in the texture of daily speech. This way of speaking extended into medicine. Long before thermometers entered the sick room, physicians judged health by touch. The hand placed on the forehead, the wrist, or the chest was the first diagnostic tool. A fever was burning, hot, or raging. A patient might be said to have chill humours, or to be cold of constitution. The framework of humoral theory, inherited from ancient Greece, explained illness as an imbalance of hot, cold, wet, and dry qualities in the body. If a patient burned with fever, it meant heat was in excess. If they shivered and paled, it meant cold had seized them. The treatment followed this logic. Hot fevers might be met with cooling diets, cold fevers with warming broths and blankets. None of this required precise measurement, only the physician's intuition. But it also meant medicine was subjective. One healer might feel that the patient was dangerously hot, another that they were only moderately so. There was no number to settle the debate. The struggle to quantify heat in the body was especially significant in the case of fevers. For centuries, fevers were among the most common symptoms of illness. They could mean infection, plague, or simply the course of a seasonal cold. Without thermometers, physicians relied on comparison to past cases. They might say, "This patient burns as hot as the one who survived last winter," or "His heat is less than that of my neighbor's son, who did not survive." These judgments were inconsistent, often fatal. The arrival of the thermometer into medicine in the 18th and 19th centuries transformed this uncertainty. For the first time, a doctor could distinguish between a mild fever and a dangerous one with precision. Numbers replaced impressions, and survival rates improved. But in the centuries before that shift, ordinary life unfolded without such measures. Architecture, for example, was designed not around numbers, but around seasonal rhythm and tradition. Houses in Northern Europe were built with thick stone walls and central hearths. Insulation was judged by experience. If smoke stayed in, warmth stayed in. In Mediterranean regions, high ceilings and shaded courtyards helped homes remain cool. Builders did not know the degrees inside a room. They knew only whether it was stifling or refreshing. Comfort was measured by sweat on the brow or the need for extra layers, not by precise readings. Clothing, too, was guided by experience rather than data. A farmer in the Alps layered wool and linen based on how bitter the wind felt that morning. A sailor in the tropics stripped to light cotton when the air grew heavy. No one knew whether it was 20 degrees or 30. They knew only whether frostbite threatened or whether heat sapped their strength. In this sense, the body was not just the measure of health, but the measure of climate. Farming, perhaps more than any other aspect of daily life, depended on temperature, yet farmers had no instruments to guide them. Seeds were sown when the soil felt warm enough to the hand. Harvests were predicted by the timing of blossoms and the behavior of birds. A late frost could wipe out a year's work, and farmers learned to read subtle signs: the thickness of ice on a pond, the way the earth smelled in spring, the pattern of dew at dawn. These were natural thermometers, drawn from experience and passed down as wisdom. Even today, sayings like "plant corn when oak leaves are the size of a squirrel's ear" preserve echoes of this tradition. Daily routines, too, adjusted to sensation rather than number. In the height of summer, people rose earlier to work before the sun grew oppressive. In deep winter, activity slowed, days shortened, and evenings were spent by the fire. Comfort was subjective, negotiated between the body and the environment. What mattered was not the exact temperature, but the lived response: when to light a fire, when to shed a layer, when to take shelter. The thermometer, when it arrived, reshaped all of this. Medicine gained a new diagnostic tool. By the late 18th century, physicians like Karl Wunderlich in Germany began charting patient temperatures systematically. He demonstrated that certain diseases followed characteristic fever patterns: typhoid, pneumonia, tuberculosis. Each had a thermal signature. No longer was a fever simply high or low. It was 38 degrees, 39, 40, and each degree carried meaning for prognosis. What once required intuition could now be mapped with numbers. Industry, too, transformed. Brewing became more consistent when yeast could be cultivated at optimal temperatures. Ironworking grew more precise when furnaces could be monitored and controlled. Textile production, glassmaking, even cooking were all stabilized by the ability to reproduce conditions exactly. A thermometer in a brewery vat or a blast furnace meant less waste, higher quality, and more reliable results. In daily life, the thermometer became a household object. By the 19th century, people placed them on walls, in gardens, outside windows. Farmers checked them to predict frost. Families used them to judge whether to stoke the fire or open the windows. Suddenly, weather could be described not just as chilly, but as 10 degrees colder than yesterday. Numbers brought comparison, memory, and record-keeping. Language itself began to shift. While poetic words like frosty and sweltering persisted, they were joined by precise numbers. Newspapers reported that the mercury fell to 20 below zero, or the heat rose above 30 degrees. Weather became measurable, shareable, standardized across cities and continents. The psychological effect was profound. Where once people relied only on their senses, now they began to trust instruments. A thermometer could declare that the room was warm even if one felt cold, or that the fever was mild even if the patient seemed flushed. In this way, numbers began to compete with sensation. Confidence slowly shifted from subjective feeling to objective reading. This was not always welcomed. Some physicians resisted, arguing that the thermometer reduced the art of diagnosis to a mechanical number. Some households saw no need for it, trusting their fires and their skin. But gradually, the authority of measurement grew. Thermometers joined clocks and scales as symbols of a modern age that valued precision and standardization. Looking back, it is astonishing to realize how recent this change is. For most of human history, people lived without knowing exact temperatures. They trusted words, feelings, traditions, and signs. It worked well enough for survival, but it left much to chance. The thermometer gave humanity a new lens, one that transformed survival into science, intuition into knowledge. And yet, there is something quietly beautiful about that earlier world. To wake on a frosty morning and feel it directly in your bones, without the mediation of a number. To judge spring's arrival by the bloom of flowers, not by a reading on a scale. To know your child had a fever not by degrees, but by the warmth of their brow beneath your hand. There was intimacy in this way of living, a closeness to nature and to one another. The thermometer did not erase that intimacy, but it changed the balance. It gave us clarity, precision, and the ability to share knowledge across continents. It allowed medicine to save lives, industry to expand, and weather to be recorded in history. But it also marked a shift from a world felt to a world measured. Perhaps both ways of knowing have their value. The language of sensation still colors our speech. We still call days frosty, nights sweltering, afternoons mild. But alongside those words, we also glance at the neat numbers on our thermometers and phones. And in those numbers, we find a different kind of comfort. The story of everyday life before exact temperatures reminds us that measurement is not just a tool. It is a way of seeing the world. And when humanity learned to measure heat and cold, we did more than invent a new instrument. We changed the way we experience life itself. We've followed the path of temperature, from the days when people judged the seasons with their skin, to the fragile glass tubes of Galileo, to mercury shimmering in sealed instruments, to the scales of Fahrenheit and Celsius that still mark our thermometers today. It is remarkable to think how something so ordinary, the number on a household thermometer, the weather forecast on a phone, the reading in a hospital chart, is the product of centuries of trial, error, and human imagination. Each degree, each scale, each careful choice of 32 or 0 carries the story of someone who sought to measure the invisible. Before numbers, warmth and cold were shared in words, frosty, sweltering, mild. Before instruments, fevers were judged by touch, seeds planted by instinct, homes built by tradition. And then, slowly, we gave heat a number. We turned sensation into knowledge, and knowledge into something the whole world could share. In that transformation lies something quietly profound. A thermometer does not just tell us the weather or a fever. It is a reminder that even the most intangible parts of life can be made visible, that what once seemed beyond measure can be brought within our understanding. So the next time you see a small column of liquid or a digital number glowing on a screen, remember the centuries of hands, minds, and lives behind it. Remember that once there were no numbers, only breath in the cold air, sweat on the brow, and the warmth of a fire. And perhaps take comfort in knowing that even in a world of measurements, there is still room for sensation, for the poetry of words like frosty and sweltering, for the intimacy of a hand on a forehead. Thank you for drifting through this story with me. I hope wherever you are, the temperature feels just right. Good night.